What's coming off around here?
Did you guys play railroad anymore today? There's a landslide, a new cut.
Hi, and just a quick note before I start discussing the DCC electrical aspects. This conversation I have for you about the DCC electronics is a bit winded, and so consequently it's taking a bit more video time than I'd actually thought it would. So what this will be is episode 11, part 1 of the DCC electronics, and parts 2 and perhaps even parts 3 will follow. There's a lot to discuss, a great deal amount of information to share with everybody about DCC, basically under the hood, if you will. This is more about the protocols and electronics than it is a discussion about how to use DCC products. Welcome to episode 11 of Fun with HO Scale Stuff. Today, in this episode, what I wanted to do is I want to present my take on what DCC is. And the DCC, in my understanding, is viewed by people in several different ways. And I think probably the most common way to view it is as some product that you can buy that will give your locomotives the capabilities of being run in a very flexible and interesting way. So you have control of the locomotive, several locomotives on a single track, and you can have control of accessories like switches or indicator lights, or even sound in the more complex states. So that's a very nice view of it, but my view's a little bit different. I look at things electronically, and so I would like to try to discuss that with everyone, but I want to try to make it clear, and I don't want to get too complicated such that it's difficult to understand. So I'm going to progress my discussion from a basic understanding of the intent, I think, that the designers of DCC had, and how they progressed to develop this very interesting, what I call protocol, is a combination of both information data packets and electronic control. So stick with me, and I'll go through the whole process of explaining it as I see it, and hopefully it's some interest to you. And if it is interesting, please like and subscribe, and maybe enjoy some more of my discussions on the electronics aspects as well as the HO scale modeling. So the way I see it, the original designers of DCC were looking at these DC models. The motors could be turned in either direction by reversing the voltages that are on the track. So your DC controller had a knob and a little switch, and the switch would go either forward or reverse. And so the motor could be driven simply by the analog voltage from the power supply. But their vision was to be able to control the model in a similar manner as you would with the analog system, but they wanted to be able to address the locomotive and do that so that you could have more than one locomotive operating on the same track. So either locomotive would be addressable. Most common in the hobby is to assign addresses to the models based on their numbers on the side of the model, the number that was assigned by the railroad. These are both Penzi units. This is an H1044 Fairbanks Morse locomotive. It's actually originally produced by, it was produced by Walthers as a DC locomotive, but somebody, not me, converted it over to DCC. So this one actually is addressable. That one is actually just a DC model. And so in order to do what they wanted to do was to make it possible to run multiple locomotives on the same track and have them be addressable, it was necessary for the designers of DCC to come up with a means to be able to tell the track itself, to send a message to just this locomotive, not that locomotive. So they had to come up with something that was both addressable, but also would maintain the power on the track, the same as the DC would. So the solution to this problem, I find it was very elegant. And so I want to talk about how they did that, the actual solution to providing an electronic signal that carried both addressable information as well as the power required to move the DC motors that are inside of these models. So just to give a very rough outline of my thinking of how this whole DCC design unfolded is that I would say that the engineers had to first consider how do we control individual locomotives. And as we said, the objective there was to make each locomotive addressable. So in their system, they had to have a signal. The signal is the thing that transmits the specific information about throttle setting, lighting, sound, all of that. So let's just say that this has a signal. So what constitutes that signal is what's very interesting about DCC. This signal has what can only be called an encoded content. So it has an encoder. So it has an encoder that's creating the information that's consumed by this locomotive. Now, what an encoder and signal would require is some form of power, energy. So we'll say that there's a power supply required, and we'll make that part of the DCC system. There's a power supply, and we know that there's an encoder. So there also has to be some control. That would be the user interface. So that goes to that, goes to that, and here we have the signal. And as far as control goes, they all look pretty much like this. They have, some control buttons that you can push, or analog wheels that can control things like speed up and down. But the one thing about the NCC power cab is that it's both of these. It has the control user interface and it has the encoder. So what comes out of the power cab is a encoded DCC signal. But the other thing that we have to talk about is that on the receiving end, we need to have some kind of decoder. And that takes whatever encoded signal is fed to the track and decodes it into a meaningful action. And it just so happens that this locomotive has a decoder. So that's the fundamental overview of the DCC control flow, if you will. But it's also an objective that the engineers were looking at is is that they have to supply a voltage power signal as well as just control signals. So here's the question is, how do they do that? Well, they want to send a speed and direction to the cab, so that they can accelerate and decelerate in any one direction. So that would be part of the encoded signal. So then this means that the responsibility lies with the decoder to actually provide the voltage to the motor and do it in such a way that it represents the desired speed and direction that was established here at the control interface. So if I say that, I want you to go forward, and then I want you to go forward this fast, that signal is being transmitted here to the track, and it's being decoded by that decoder. All right, so there is a signal that must be generated by the engineers in order to encode a message onto this track that's received by the locomotive, and to be able to supply a voltage to power up the locomotive and its decoder. So how did they do that? I'd like to talk first about the encoding aspect. Most historically, encoding is anything where if you have a signal, like military has signals from one ship to another where they flash lights, and they use a thing called Morse code, and the code simply represents words in a series of long and short bursts. That's the same thing that can be said about the code used to represent a signal that was placed on a serial interface. There's some collection of long and short bursts that represent that signal, or the content of the signal, pardon me. So the thing that what is typically talked about are ones and zeros, just because we live in a digital age, but it could be long and short, it could be on and off, but we'll go with ones and zeros. And let's say that a particular duration, such as this duration, is short, and that's a 1. So we'll just call that a 1. And then we'll take another one, and we'll make it longer in duration, and we'll call that a 0. So if I have these different durations that are being transmitted onto this track, then something receiving signals from the track could see a series of ones and zeros. Simple enough. The thing that many times are on, say, digital circuitry, for example, that's done, is that there's a clock, some clock, that's constant, and then there's another signal that's changing with the clock, so that there's a 1 and there's a 0 on a signal line. But you can't do that with this track. It would require 2 separate signals plus a neutral, which is a third signal. So it has to be some combination. What they have done typically with like serial interfaces like RS-232 or RS-45 interface, they have a transition somewhere within the duration. So there's a transition, and that whole signal then becomes a 1. And then there's another transition, and then that whole signal becomes the 0. So you have to have a transition so that the receiver can detect the start and stop of the duration that's coding some bit of information. So as this collection of bits come together, then you would have what would then be called a packet. So the packet would be that collection of ones and zeros, such as that, where you have like you have a 1, 0, 0, 1, 1. And that could represent anything. It could represent a letter of the alphabet or a command, for instance. Now, with any kind of protocol, you can't just be bursting transitions onto a serial interface because it wouldn't make any sense to the receiver. So what is standard on serial interfaces is the thing called a preamble. So a preamble could be a fixed succession of, for instance, ones. So let's say I have to have, 5 ones. So 5 ones is a message to the receiver that what follows then is a coded message. So it sees that and says, oh, okay, you're talking and you're sending a packet. So it wants to see this packet then after it sees this preamble. So we had a preamble and we have a packet. So these working together, oftentimes you could say are a complete packet or a complete message to the track. You'll notice that the concept that I'm presenting here is pretty much just DC. For instance, there's some ground reference, let's call it ground, and then there's some V plus reference, and then things are transitioning between the two. So that will not work well with an electric motor, that because it's a nutty frequency when you start changing the ones and zeros around, and the motor would probably just get very hot and vibrate and make a lot of noise. So what needs to be done for the sake of a signal to a decoder would be to take our signal, let's talk about the signal as a voltage. So there's some V plus and there's some ground reference, okay? Well, we're going to get rid of the ground reference and we're going to just say there's some V plus and there's some V minus. And then somewhere in between here is a ground or neutral, that these signals, these signals that are generated in a serial fashion will fluctuate both above and below this neutral reference. And a neutral reference then would have to be established, well, at the source where you have the encoder, it uses its own ground. It uses its own neutral reference for its DC signal. How does it do that? We'll get into that. We'll talk more about how it does that. So the encoder takes care of creating this odd signal that fluctuates both above and below ground reference. On the flip side, the decoder has no reference at all, and so it has to generally figure out what is the center point of the two signals. So as long as you're streaming some signals that are going above and below some neutral point, the decoder can take an average of the difference of the two signals and then determine what the center point of that voltage would be. So using a voltage divider. So it would just simply it would be responsible then to have some kind of a circuit. And again, and we can talk about that, but this is what what was devised then for DCC was this type of coding, this type of coding of the ones and zeros. So if that's a 1, and then there would be, as we said, a 0. And so this high and low signal then is called an AC signal. But the fact that it's a sharp rising and falling edge, it's also generally referred to as a square wave. So most everybody, when we talk about AC, you're used to similar to a signal at your power outlets that look like that for 120 volts, and it has some neutral reference. A square wave is it's very different from an AC signal, because an AC signal frequency is pretty much what it says it is. Like this signal here is going to be 60 hertz. And it's always going to be 60 hertz. So there's 60 hertz is 60 transitions per second. So or 60 cycles per second. With a square wave, all bets are off. If you did, I don't want to get too technical, but the frequency required to get a sharp rising edge is extraordinarily high. It takes a whole lot of frequency to make a sharp edge. So these edges aren't really that square. They're probably more like this when you look at them on a scope. And so there's some slant to them. And then there's again slant back down again. And there might even be some ugliness to the signal. For instance, it might look like this. And then down and back up again. So that's possible. It's just called overshoot. But these things are not, we're not going to talk about that for this, just that you're aware of the fact that these signals aren't perfectly square, but they are essentially square, and that's what we care about. So we say we've got a square wave that's an AC signal. And that kind of puzzles some people because, like I say, they're so used to an AC signal as being this nice, smooth transitioning sine wave, but that's just not what the engineers decided to do for DCC. So what's going to happen then is that the signal to be generated by the encoder is going to be doing, like I say, using its own ground reference, and then the decoder is going to be taking some kind of average of the two signals, high and low, and calling that a neutral. So it can say, okay, this one was high, this one was low. Now we get a little bit, we'll talk right now about what's the power. Geez, I'm running out of paper. Well, we'll do it this way. How does the DCC apply power to the track if it's putting a square wave that's an AC signal? Well, in the decoder, it sees this signal and it's established some neutral region on it by taking averages of V plus and V minus. Sorry, I'm a little sloppy. And this it says, okay, this is going to be high, that's low. But what it then does with that signal is it passes it through a diode so that the signal, in effect, like let's say we've got, maybe I showed up myself here, we'll do it here. We've got some of these AC square waves coming in, and they look kind of like that. And it's got some neutral reference that has been established by the decoder. And then the decoder adds, it's going to add in this diode. So we've got some kind of diode in the circuit, right? And given that there's a diode somewhere, what happens is that for currents that are above on the higher voltage, these currents are going in one direction. And then for the currents that are in the negative, those currents are going in the opposite direction. So when you put a diode, or actually a bridge configuration of diodes to pass the currents, you rectify the currents so that they all go in the same direction, and the signal you get is this signal. That, in fact, is this part of the signal has been rectified to this portion to a positive voltage, and again here, and so on throughout the entire train of signals that are on the DCC track. So we then have this final configuration, and I'll show you some little more detail about the circuitry. But I'm going to first talk about, if you fully grasp the idea of an AC square wave and it's being rectified, we'll move along, and I'm going to show you some circuits that can function to both produce that AC square wave and also to decode the AC square wave. And I'll start with producing it. Well, welcome to the end of Fun with HO Scale Stuff, Episode 11, Part 1 of DCC Under the Hood. Thank you for watching, and if this was at all interesting, even a little, please feel free to leave a like. And if you haven't already subscribed to my channel, you're invited to go ahead and do that. I appreciate all of your feedback. So if you have any comments about what's been presented or questions, please leave the comments in the space below the video, and I will be responding to you as quickly as possible. Do appreciate everything that people have offered to the channel. It's all been good. Looking forward to giving you the next episode, which is going to be a bit of a discussion on circuitry and the protocols used with DCC. Oh, you want your mommy?